which is this tool called Juliet. I entitled this talk Exoplanets with Juliet, and like in the background you can see one of the fits that was done with Juliet 2, which was one of the first GLOGST data sets that we analyzed with this. And it's a really neat tool that has been of use for people that do rare velocities, for people that do photometry, not only rare velocities for exoplanets, but also for stellar characterization people. It has been pretty useful, transits, rare velocities, and more. So it's a pleasure to be giving a talk about this tool here. So first of all, let me go with the main item on this, like what is this Juliet tool? So first of all, the Juliet is not an acronym, it's a name, and it's like a variation of the name of my daughter in particular. And it's a tool that, first of all, it's a Python library. It's easy to install, pip install Juliet, and that's it, you're set to go. And it's very, very useful, and it can easily model photometry and rare velocities, meaning photometry from like typically relative photometry, like for transits, eclipses, and more. And the whole motivation of this was to have like a one-stop shop with which you can model all this with a ton of samplers. So I'm really a fan of different sampling techniques that I'm going to be mentioning in a bit why. And also all your favorite models. It can do transits, it can do eclipses, it can do Gaussian processes, it can do linear models, and so on. So there's a ton of modeling that you can do with this, that we have coded this in such a way that we hope it's intuitive. It can be included into your own pipeline, so that's why it's a library. So the idea is that it forms part, if you want, it forms part of your day-to-day usage in exoplanet science. So using Juliet is as easy as ABC. I don't know if we will tell it. So there's three things you need to do if you want to get to use Juliet. It's basically 3 steps. So suppose that you want to fit some test data. And the neat thing about Juliet, it has some very handy tools to download data, for instance, from Juliet right away. So the first step, it's from the ABCs, to assemble your data. And the way you assemble your data, it's basically in dictionaries. So Juliet loves dictionaries, and that's very useful for pipelining because you can make dictionaries work with basically any kind of data you have. So what this line of code here does, right? So we are calling this juliet.utils.get all test data. It's just an easy way to download data from MAST for the LP 700-9118 system. And what this downloads and what this stores is these 3 dictionaries, T, F, and FR, which is the time, the flux, and the error on the flux. And it's not only the error on the flux for a given observation, it's like actually 2 observations from tests from 2 sectors, from sector 9 and sector 36. And that gets neatly stored here, but also you can store it in your own way. If you have your own data in like a text file, just convert that to these neat dictionaries that Juliet understands. And that's it, you're set to go. That's how you set your data set. So these will look like this, basically. If you plotted these data from these dictionaries, you have relative flux versus time from these 2 sectors. All right, so that's the first thing. So you assemble your data with Juliet. Now, how do we actually fit it? So that's the B in this ABC, is to bound and define your priors. So basically, you have to define priors for your fit. And this at first might seem a bit daunting, but actually it's pretty, once you get the hang of it, it's pretty intuitive because there's 3 main parts that you have to define. So first of all, there's a set of parameters, names that you define. That's the top line here in these yellow encircled things. So for instance, here I'm defining the uppercase P, which in the Juliet language is the period of the planet. You know that there's a P1 underscore P1 and underscore P2 in the parameter names. And that's because you can do multiple planet fits. In particular, this LP791 system, it's a multi-planet system. It has at least two planets in the system. And here we're setting a Juliet fit to fit both of them simultaneously. So in this case, you assign the parameter names. That's the first set of array that I set here in the params array. The dists array set the distributions of those priors. And at the bottom, you set the hyper parameters for that prior. So in this case, I'm encircling the period of the planet, that I'm setting a normal distribution of planet 1, that I'm setting a normal distribution of like 0.9 with a 0.1 standard deviation. So 0.9 is the mean of that normal distribution, 0.1 is the standard deviation of that distribution. And then I do the same for the other parameters. So for instance, here, I do the same for the time of transit center of planet 1, and so on. So again, as I was mentioning before, there's priors for planet 1 and planet 2, which are defined by this underscore P1, P2. And neat things you can do, you can choose different parametrizations. All of this it's on the Juliet documentation. I'm going to go in a little bit in time. But for instance, here, because I have a 2-planet system, instead of fitting the scale semi-major axis in this case that you would need to do the whole Keplerian solution, we're using the stellar density, which should be common to both planets, and that you can also fit for that in a Juliet fit. In light curve fitting, you also need to do some limb darkening. And in this case, for instance, one of the neat things that Juliet includes is the fact that you can do common limb darkening coefficients across instruments. So for instance, in this case, this is sector 9 and sector 36 data from TESS. And this is the same instrument. It's the same, basically, detector. It's the same optical path. So you should have all around more or less the same limb darkening coefficients, unless something happened with this stack. We're assuming that didn't happen here. So you can link parameters together. In this case, I'm linking the sector 9 and sector 36 limb darkening coefficients, that it's just one set of coefficients that are fitted for both data sets. As I was mentioning before, there's a wide array of priors to choose. It's not only the normal distribution that I just gave the example for. Again, this is all in the documentation, but it's also very easy to incorporate new distributions. In fact, some of the developers that are contributing to Juliet, they have implemented their own priors too. So if you have your own prior that is not in the set of Juliet ones, it's very easy to implement. So once you set all this, you see it's like a 2-step process so far, A and B, assemble your data and bound your priors. Then that's it. You just combine everything and fit. And fitting is a breeze, right? So it's these two, you know that I've added only these last 2 lines of code here, which is you just load the data set. So you load the priors, you load the light curves, you define an output folder, and then you do dataset.fit, and that's it. You get like a complete fit of your data. So in this case, we fitted, the idea of this script is that you can just fit in this entire set of data set from TESS in like, you know, a couple tens of lines of code. So it's very easy with like a very complicated priors and everything. So once you've done this, you know, you will go, you will perform your fit, and checking those results with Juliet is also a breeze. It's like basically a 1 line of code to do that. So suppose you did the fit, as I just showed you, and now you want to check the data and the fits, right? So to do that, it's very simple. There's these 3 lines of code. It's only 1 line of code from Juliet, which is the middle one. So first I plot the data. That's the first one. The middle one is just evaluating the light curve results from your fit. So it's this results.lc.evaluate. So you can evaluate the model from, in this case, the sector 36 data, and then you just plot that model. And that's it. It's just as easy as ABC. You get these very neat fits to the test data. So you see these little thingies going down. Those are the transits. So there's planet 1 and planet 2, the small planet and the planet that produces the small transit depths, and the planet that produces large transit depths. And I'm going to do a close-up here. And you can see how Juliet neatly handles these multi-planet systems too. So, you know, it's very easy to actually fit your data set and make it as complicated as you want and include as many instruments as you want and so on. So the neat thing is that Juliet is fully documented and it's under active development. I'm very proud to note this in the right-hand side where you see the GitHub. There's used by like 11 people. I mean, there's much more usage, but the contributors part is pretty interesting. There's many contributors that have been part of Juliet now. It's a screenshot from last year, but the latest release actually happened last week. We try to do basically 2 releases per year at the very least. We're trying to bump that up to quarterly now. But the latest release, for instance, from Juliet, were some improvements that were made by some developers, from Juliet developers, from the community. So for instance, now we support with Juliet multi-instrument transit and eclipse depths. This is particularly interesting for people that do like transit spectroscopy, for instance. So you can have each of the wavelengths fitted together with all your system parameters if you wanted. I'm going to explain a little bit that you can do limb asymmetries. That's the second one that we've implemented, and there's other extra implementations that just happened. So let me go through a little bit of what Juliet can do for you, for your science. So I mentioned before, there's a lot of stuff that you can do. Gaussian processes, you can do transit time and variation. Again, all of this is in the Juliet documentation, but I wanted to go through some highlights on this. The first one I wanted to go through was a model comparison. I'm crazy about this stuff. And this is very easy to do with Juliet because it uses a wide array of samplers. In particular, the samplers that Juliet supports right now are classic MCMC, which is just the main objective is to sample from the posterior, but it also uses nested sampling that allows you to compute an actual log evidence. So there's a bunch of samplers that we're supporting right now. And again, it's very easy to add your favorite sampler to the list. So if you have it, just create an issue and then we can make it happen. But I wanted to go briefly on why this is so important and why model comparison is such a neat thing. And the neat thing is that with nested samplers, you can extract the Bayesian evidence to perform model comparison. And the whole idea is that the end goal that you would want to do model comparison is to compute this ratio. So you have two models, model 1 and model 1, and you want to compare the probability of model 1 given the data over the probability of model 2 over the data. And that's actually very hard to do. You know, how much more likely is model 1 over 2 given the data? It's actually a complicated integral to develop. But the neat thing is that you can transform that by Bayes' theorem to these terms here. And in particular, so the right-hand side, the probability of model 1 and model 2, those are the priors of the models. But the ones I want you to put attention to is the evidence, this probability of the data given the model. And those evidences are very hard to get, but nested samplers get them for free to you. That's actually the objective of nested samplers that Juliet has within the array of samplers that it supports. So the neat thing is that you can just obtain that. You can put your own priors for the models. And given Juliet reports you the log evidence, you can do this model comparison on your own. So you can compare light curve models. You can compare, you know, doing one limb darkening coefficient to another. If you're doing rate of velocities and you're not sure if you have one planet on your data set or two planets in the data set, then you can do this model comparison with Juliet on its own via these Bayesian evidences. So it's pretty neat. The other thing that I wanted to highlight, which is kind of new, is this inhomogeneous limbs that we just implemented in Juliet. So this is the idea that when you do normal transit spectroscopy, you know, when you model the planet as passing in front of the star, and you expect some starlight to go through the atmosphere, people have been doing this normal transit spectrum in which the transit depth, like the radius of the planet, varies as a function of wavelength as different absorption features show up at different wavelengths. But there has been this idea that maybe the two sides of the planet could be also different. And there has been many ways to parameterize this along the way. And in particular, we implemented one such possibility with a package we call Catwoman. It's like, you know, that for light curves, there's this Batman package. That's why we decided to go with Catwoman name. That the amazing Catherine Jones implemented in Python/C. And the idea is that it allows to fit, you know, two semicircles on top of the star instead of just one big circle. And it's very easy to implement, to use Juliet to implement this Catwoman model. So this was the model that I was just showing you before for the LP791 system. So to implement Catwoman, it's simply adding these two extra parameters, which are like the size of these semicircles and the angle between the semicircles, because, you know, the axis might be of the planetary axis might be rotated with respect to the line of motion. So you can add this and you can just do it with your own data and, you know, go crazy analyzing data with this. So as you see, there's a lot of stuff to do. I mean, 20 minutes doesn't cut it to showcase everything that it does. I particularly focused on light curves because that's the easiest that you can gather data for. It's very easy with Juliet to gather data from tests to do light curves and so on. But again, this can do rate of velocities. This can do like long-term photometry, not even for if you don't even have transits, you can still do long-term photometry. You can fit it with like Gaussian processes and so on. So there's a lot that you can do. Again, all of that in the documentation. I think it's very well explained. So it's a little summary. First of all, Juliet is a neat, I think, easy to use modeling tool for transiting exoplanet science and for rate of velocities too. So it's documented and under active development. It can handle the usual problems like transits, eclipse, Gaussian process, linear models, and some of new complex ones. It has a nice selection of samplers that you can aid on model comparison via Bayesian evidences. And I think it has a ton to offer for your science. As an end slide, I can send these slides to Joe and he can upload it, but there's a lot of notebooks that I created along the way. And it's 3 highlights out of what you can do with Juliet in particular for transit spectroscopy and for transit photometry. There's a notebook here that I have on using it with test data, analyzing real GWST data, analyzing HSTS data too. So if you want to get a hand on that with Juliet, go crazy. It's a neat tool, and I'm happy to be sharing it here and with the world. That's it.
Awesome, Nestor. Thank you so much. It was a great talk going through something that can do so much in such a short period of time. So thank you for highlighting everything. So yeah, we have time for a few questions. If anyone has any questions, feel free to raise your hand on Zoom, or you can also post them in chat and I can read them off. To get out, I think we see one here. Sabina, do you want to go ahead and unmute?
Yeah, I have a question. Hi, it was a really nice talk. I'm curious if you looked at how fast it is to fit the transiting models comparing to codes like Batman and Starry and Exoplanet, because we have so many of them.
Right. So is your question how does Juliet compares against these other codes? Is that the question?
Yes.
Yeah. Okay. So in terms of the comparisons with like Batman and Starry, which are codes that actually generate light curves, we make use of those. So you can see Juliet as like a compilation of those codes. Because, for instance, the light curve models that we use here, they come from Batman. Or in the case of the asymmetric limbs that I just showed, it comes from Catwoman. So Juliet uses those light curve models in doing its thing, right? In doing its modeling. So we take advantage of the fact that these beautiful packages exist to generate light curves, and we use them. And right now we're working on implementing some Starry models to Juliet, for instance, to do like phase curves and so on. As compared to Exoplanet, Exoplanet does a similar thing that what Juliet does, in the sense that Exoplanet allows you to model and package your modeling on its own. We have different kind of philosophies on what we optimize in terms of the samplers, for instance. Exoplanet uses this Hamiltonian Monte Carlo that we also want to implement here in Juliet eventually. But here we leave it mostly to the user if they want to use like normal MCMC or nested samplers. I typically prefer for nested samplers, just make a more efficient exploration of the parameter space, in my opinion. But yeah, in that sense, they're very similar tools. Actually, they were out in the open in pretty similar times. So we have like similar ideas of this at similar times. And it's a matter of taste. Like if you like more the modeling perspective that Juliet provides for you in terms of defining your models and defining your fit, like this one, you go with Juliet. If you like the Exoplanet one better, you go with Exoplanet. But they're both flexible tools that do similar things. But again, Juliet has its own things too, allowing for these Catwoman models and others that we're constantly implementing, and so on. So Exoplanet, I think, uses Starry basically as its light curve model only. So there's other tools out there that are similar too. But I think Python-wise, I think Exoplanet, Pianetti, and Juliet are all pretty similar in that regard. So yeah.